So for those of you that did the quiz was essentially an introduction to the power rule. So there is a rule. Actually, let me back up a sec. Before we talk about rules, let's talk about some notation, because there's some notation that I'm going to use and the professor's going to use, and it can definitely, there's multiple notations that are acceptable when taking a derivative. So I feel like we should kind of make sure everyone's on the same page as far as what we can say. So let's say you had some function. Let's say we had y or f of x equal to, I don't really care what it is, 3x squared plus 2. There is probably 5 good ways you could write the derivative of this. You could write y prime. You could write f prime of x. You could write dy dx. You could write d dx of f of x. You could write d dx of the actual function 3x squared plus 2. You could probably write 3x squared plus 2 prime. And these are all, oh, yeah, sorry. The last class I taught is still converting, and I have to let it convert. And so maybe I'll just say some words for a few more minutes before we get going, because I need that. Normally I would just cancel it, but I want to post the video for my students in that class later on. So I will just have to wait a minute while it finishes converting here. It's because I went a few minutes over, and so it's taking a little longer. Yeah, that happens sometimes. I apologize. My computer only has so much power. Yeah, no, it's definitely me, everybody. It's not you. It's not you. It's me. So what can I say while we are waiting for the last 8% to finish converting here? Well, good question. So there are lots of notations. I can type them. So if you have a function y equal to f of x, there are many notations for the derivative. There's y prime. There's f prime of x. There is dy dx. Not a fraction, but it acts like a fraction in pretty much every reasonable way. So we mostly treat it like a fraction, even though it is technically not a fraction. And then you have d dx of f of x. Okay, I just stopped converting finally. Cool. Yeah, go away. Okay, hopefully I am not super blurry now. Can you guys see me all right? Am I bored? Yes, no, good, all right. Excellent, yeah, sorry, I'll have to be better about ending my other class on time so that we do not have the overlap of converting and having another Zoom meeting. So, as I was saying, we're going to talk about derivative rules, but before I get there, I just want to make sure everyone is cool with all the different notations you can have. So when you're writing, your function as y or as f of x or as actually what the function is, there's like a lot of ways you can write the derivative. You can write y prime, you can write f prime of x, you can write dy dx, that's the derivative of y with respect to x. You can write d dx of f of x, the derivative with respect to x of the function f of x. You can even write d dx of 3x squared plus 2. We do, which is the derivative with respect to x of 3x squared plus 2. And you can also write 3x squared plus 2 prime. I should point out, the correct way of saying this is not dy over dx, it is dy dx. We don't say the over part because it's not really a fraction. Same thing here. We don't say d over dx f of x, we say d dx of f of x because we are taking the derivative d dx of the function f of x. So I always encourage my students to say things correctly, use the proper nomenclature and names and notation, and I will definitely try to demonstrate that for you all as we talk about things. What else do I want to say about this? I don't think anything just yet. So that said, there are lots of ways of asking you about a derivative of a thing. So I might say something like, for the function f of x equal to x to the third, find the derivative. That's a lot of writing to get to the point. Most people, myself included, instead would rather write the following. Find d dx of x cubed. This is the same question with a lot less writing, right? I'm still telling you what the function is, it's x cubed, and I'm still asking you to take the derivative of it. So my guess is that a lot of your teachers will probably write things like this because it's easy and it's convenient and it's fast. But it still means the same thing as this. If you're given a function, take the derivative. And maybe, I feel like the prime is not showing up very well. Let me make that a little more clear. Right, that says f prime of x. Seems like that's a little more visible. Okay, now for those of you that did the quiz, or even those of you that didn't, you guys all saw that the derivative of x cubed is 3x squared. And we are certainly moving towards, or have moved towards, or have gotten past already, talking about the power rule, which is the rule that says if you have x to a power, the derivative is that power times x to the one less power. So the power rule more generally is written as, you can either write it, so I would probably write it most easily as the derivative d dx of x to the n is equal to n times x to the n minus 1. Or if you wanted to, you could write it as for f of x equal to x to the n, f prime of x is equal to n times x to the n minus 1. And this is true for any n value. For any real number n. Now, your teacher might ask you, or might have shown you, something about this with the limit definition. So I could also say, find the derivative of x cubed. Now, if I just find the derivative of x cubed, if someone says just find the derivative, they don't give you any more instruction, you should assume you're allowed to use whatever rules you've learned. But if someone specifically says, using the limit definition of the derivative, then we have to do the whole thing. The thing where you do the limit definition. You say, oh, the derivative d dx of x cubed is equal to the limit as h goes to 0 of, so I would write f of x plus h minus f of x, so they don't have anything called f of x. So I'd have to say, oh, I'm going to say that f of x, I've kind of lost room here. I'm going to let f of x be x cubed. So that I personally can write this as f of x plus h minus f of x all over h. A lot of people like to skip this step. That's fine. It's a limit as h goes to 0 of x plus h cubed minus x cubed all over h. And again, I know this is old news for most of you. Most of you did this in the quiz. Great. The thing we have to be careful about for anything, really, is making sure we do the algebra right. X plus h cubed multiplies out as x cubed plus 3x squared h plus 3xh squared plus h cubed. And then we got the minus x cubed. If you want, I'll show you a shortcut on how to do that in just a second. All over h. The x cubes cancel. Everything else has at least one h in it, so we can divide just by h. I like to factor out an h, really. From the top, I would factor out h. I'd have 3x squared plus 3xh plus h squared. Then those h's cancel. And then you can see that the rest of the things, well, I get 3x squared. And then h goes to 0, so I get 3x times 0 plus 0. Notice that so I want to be very, very specific here. Every step, I've written the limit as h goes to 0, because every step still has h's in it. So still I'm asking, oh, for this expression, which has h's in it, what happens as the h values approach 0? And then in this last step, I'm saying, okay, now the h values are actually approaching 0, and here's what happens. You get 3x squared plus 0 plus 0. So I'm no longer writing the limit here because I'm actually taking the limit. So basically, if you still have the variable in your expression that your thing is that your limit is has like the limit as h approaches something, if you still have h's, you should still be writing the limit. If you no longer have h's, you should no longer be writing the limit. Same goes if it's x approaching something. So here. You can do the same sort of thing for any, well, actually, we also said in the exam, so I said this, and you guys might not believe me, that's all right. I said that x plus h to the nth power, if n is a positive integer, is equal to x to the n plus n times x to the n minus 1 times h plus n times, sorry, not n, plus some other weird number, n times n plus 1 over 2 times x to the n minus 2 times h squared, plus, and then it went on for a while, and then you got some last couple things. You got n times x times h to the n minus 1 plus h to the n. Unverified, I just said it. I don't know how much you guys really care, but this is kind of an interesting formula. One way you can see it is from Pascal's triangle. So let me show you guys some things. Some things that might seem kind of dumb for just a minute. Okay, x plus h to the 0th power, I know is not very exciting, just one. And x plus h to the 1st is just x plus h. And x plus h squared, not particularly exciting. It's x squared plus 2xh plus h squared. And x plus h cubed, definitely not just x cubed plus h cubed. There's some middle terms. It is x cubed plus 3x squared h plus 3xh squared plus h cubed. And this pattern goes on. Well, pattern, I sort of haven't really talked about pattern. So the pattern of coefficients, so there's a 1x here and a 1h there. There's a 1, a 2, a 1, a 1, a 3, a 3, a 1. Those come from something called Pascal's triangle, which is where you start with a 1 at the top and then some 1s down, and you get basically 1s on the outsides of the triangle. And then each middle term, you get by adding the upper two things. So like 1 plus 1 gives you 2. And then you get a 1 on the outside, and then 1 plus 2 gives you 3. 2 plus 1 gives you 3, and then a 1. And you can keep going. 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. And what's interesting, well, one of the things, there's actually a lot of interesting things about Pascal's triangle. But one of the interesting things is that each row of digits corresponds to the coefficients in this binomial expansion. So these are called the binomial coefficients, and they come from taking this thing that's 2 terms to a power and multiplying it out. So I know from Pascal's triangle that x plus h to the 5th is 1 times x to the 5th, plus 5 times x to the 4th times h, plus 10 times x to the 1 less power, which is x cubed, times h to the 1 more power, which is h squared, plus 10 times x squared times h cubed, plus 5 times x times h to the 4th, plus 1 times h to the 5th. And you can do that for anything. So like, if you wanted to, you could say like, well, what's x plus h to the 7th? Well, I need to go out to the row where 7 was the second term. So 1, 6, 15, 20, 15, 6, 1, and then 1, 7, 21, 35, 35. There is symmetry. So exponents to the 7th would be x to the 7th plus 7x to the 6th, h to the 1st, plus, it's a lot of writing, 21x to the 5th, h squared. And so each next term gets the next coefficient, and the power of x is 1 less than the power of h is 1 more. And it goes on. Now, here's what ends up happening with this. This one's too long. I picked too big a number. Oh well. 21x squared h to the 5th plus 7x h to the 6th plus 1 h to the 7th. So let's say I wanted to use this to find the derivative of x to the 7th. Well, I'm not really going to do it. I'm going to kind of do it. I'm really just going to talk it out. So let's say I wanted to find the derivative of x to the 7th using the limit definition. We already know what the answer is going to be. We know the answer is going to be 7x to the 6th. But if we want to use the limit definition, here's why this happens. And again, a lot of you said this on your quiz. A lot of you probably saw this in the quiz. You're going to get this big mess here. So it's going to be x plus h to the 7th minus x to the 7th all over h. Right, there's my f of x plus h minus my f of x all over h. Now I'm not going to write this all out again because that seems silly. But I'm going to write the following. Limit h goes to 0 of x to the 7th plus 7x to the 6th, h to the 1st. And then I have a lot more terms with higher powers of h. Right? I have something times x to the 5th times h squared plus something times x to the 4th times h cubed plus all the way to the last couple terms, which are 7x h to the 6th plus h to the 7th minus x to the 7th all over h. Here's what happens every time. The x to the powers cancel. And then you divide everything by h. So you get the limit as h goes to 0 of 7x to the 6th. And then everything else has h to a power that's higher than 1. So everything else has something with an h in it. Something times x to the 5th, h to the 1st, plus something times x to the 4th times h squared, plus all the way to 7x h to the 5th plus h to the 6th. And all these terms that have h's, all those go to 0. And so you're left with just 7x to the 6th. So, power rule. We can prove it for any power where the power is a positive integer, because you can use this expansion. We can't really, I mean, there are ways to prove it, but they're very complicated, or at least compared to this, to prove it for powers that are, to prove it for any power of x as opposed to just a positive integer power of x. But we can certainly show that it's true for some other powers. So let's use the power rule. Let's say I want to take the derivative of, I don't know, x to the 82nd. This is going to feel silly. I mean, I don't know. It feels silly to me because I've done this so much, right? Like, I'm like, well, yeah, these power rules are easy. But again, I should remind myself, this might be new for some of you, right? Maybe it's not super easy. So let's do some examples. Derivative of x to the 82nd. 82 times x to the 81st. Right, I'm really just throwing it into that formula. Or the derivative of 1 over x to the 9th. To be careful here, it's not 1 over 9x to the 8th, right? To be able to use the power rule, you have to write it as x to a power, not in a fraction, not in a root, not in an exponent, right? You have to have just the derivative of x to some power, x to the negative 9th. That's going to be, well, again, we're going to use the power rule. So you get negative 9 times x to the 1 less power. Negative 9 minus 1, which is negative 10. I do want to point out, in this first step I simplified. I still wrote d dx because I still had to take the derivative, right? I'm just rewriting the derivative of 1 over x to the 9th is equal to the derivative of x to the negative 9th. Because these two things are the same, I'm still taking the derivative of them. Then in the next step, I took the derivative. So I'm no longer writing the symbol that means take the derivative because I did the thing that this symbol told me to do. So how do we know it works for negative numbers? Well, let's do an example. We know, or at least we think we know, that the derivative of x to the negative 1 should be negative 1 times x to the minus 1 minus 1, which is negative x to the negative second. Or written in maybe a more digestible way, the derivative of 1 over x, which is the same as x to the negative first, is equal to negative 1 over x squared, which is the same as negative x to the negative second. We can use the limit definition here. It'd be very challenging, although not impossible, to use the limit definition for 1 over x to the 9th. It'd be very not fun. It'd be, that's not true. It would be all right. It would be gross, though. We can definitely do it for 1 over x. Let's see here. So limit as h goes, sorry, I want to find the derivative of f of x equal to 1 over x using the limit definition. So we limit as h goes to 0 of, again, f of x plus h minus f of x over h. So we limit as h goes to 0 of 1 over x plus h minus 1 over x over h. Then we're going to multiply by a common denominator. So I'm going to multiply the top and the bottom by x plus h times x. And let's see. If I multiply here, I get x, because the x plus h is canceled. When I multiply here, I get x plus h, because the x is canceled. The bottom is still not really changed. It's h times x plus h times x. And then you get the limit as h goes to 0 of, so I subtract, x minus x is 0. The minus distributes, I get a minus h over h times x plus h times x. This h cancels with not that h, that h. And I get the limit as h goes to 0 of negative 1 over x plus h times x. Then I take the limit by letting the h's that remain go to 0. So I get negative 1 over x plus 0 times x, which is negative 1 over x times x, which is negative 1 over x squared. Or negative x to the negative second. So we see, at least in this one example, that the power rule does work for a negative power, right? Because our function really was x to the negative first. So power rule definitely works for negative powers. Now I know this is not a proof of that, but this is an example like, oh yeah, here is one negative power works for. The power rule, well again, I'll say that the power rule works for all powers. We know it works for positive integer powers from the quiz and from what we did on a page I erased. We also know, well, it also does, I should say, work for fractional powers. And again, really, I should just be saying it works for all powers. But I want to show you it works for fractional powers by using the limit definition. So here's what we think should happen. If my function is x to the, yeah, let's have some fun. Let's say it's x to the 1/3. I'm going to do something different first. Yeah, this is going to be kind of a pain. It's all right. So first, before I, yeah, let's do that. So before I answer this question, before I find the derivative, well, first of all, just using the power rule. we know the derivative should be 1/3 times x to the 1/3 minus 1, which is 1/3 times x to the negative 2/3. So the question I want to answer first is this function differentiable? Now, again, I don't think it's good to ask the question that way, because if someone says, is a function differentiable, what they usually mean is it differentiable everywhere? And so then you have to hunt for the place where it might not be differentiable. I'm just going to get to the point, pun intended, and say, is f of x differentiable at the point x equals 0? Because that's really where I'm curious about. So you have two options, depending on where you're at in your class. You can either take the derivative and say, well, does it exist at 0? So does f prime of 0 exist? Well, let's try and plug it in. F prime of 0 is 1/3 times 0 to the negative 2/3 power. Okay, this is kind of a trick question. What's 0 to the negative 2/3 power? Everyone's like, oh, he wants me to respond.
Is it 1 or 0?
It is, so 0 is the guess I was expecting to get, but it's not 0.
Is it not
also not 1. So the answer is it actually doesn't exist, because the way you should really be thinking of a negative power is dividing by the same positive power. So I'm really thinking of this as 1/3 times not 0 to the negative 2/3, but 1/0 to the positive 2/3. And then it'd be perfect. By the way, I appreciate the responses. Like, thank you for guessing. Please respond, even if you think you might be wrong. It's okay to be wrong. 0 to the 2/3 is 0, because 0 squared is 0, and then the cube root of 0 is 0. But 1 divided by 0 blows up, right? It gets infinitely large. So this is not defined. And I want to really emphasize that. When you get 0 to a negative power, you're dividing by 0. So that's why I, most of the time, really encourage people to rewrite 0 to a negative power as 1/0 to the same corresponding positive power, because it'll make it a little more obvious that, oh, that's division by 0. Ah, damn. Dropping red pen on the carpet. Well, that's great. Oh, wow.
So if it was 0 to a positive power, would we be able to solve that?
Should I say that one more time?
If it was 0 to a positive power, would we be able to solve that?
Yeah, if it was 0 to a positive power, it'd be 0. So, for example, if I asked, is f of x equal to, say, I don't know, x to the 4th differentiable at x equal to 0? The answer would be definitely yes, because f prime of x is 4x cubed, and then you can plug in 0 and say f prime of 0 is 4 times 0 cubed, which is just 0. So one way you can show a function isn't differentiable at a point is take the derivative and try and plug in the point. It doesn't always work, but it works a lot of the time. And obviously try and plug it in and have it not exist. The other way, though, is to use a limit definition. Say, okay, I want to find f prime of 0 using the limit definition. So we know, I'm going to back up one sec. We know that f prime of x is the limit as h goes to 0 of f of x plus h minus f of x over h, which is equal to the limit as h goes to 0 of f of x plus h is going to be the cube root of x plus h, or x plus h to the 1/3 power minus x to the 1/3 power over h. Now this is challenging to deal with. We will in a minute, but we don't actually have to deal with that here, because what I'm actually asking isn't what the derivative is everywhere at x. I'm asking specifically what the derivative is at 0. So we say, oh, f prime of 0 is the limit as h goes to 0 of f of 0 plus h minus f of 0 all over h, right? If I'm trying to find the derivative at a particular point, I replace x with that x value. So I'm getting f of 0 plus h minus f of 0 all over h. And in this case, I'm going to get the limit as h goes to 0 of f of h, which is just h to the 1/3, minus f of 0, which is 0, right? 0 to the 1/3 is 0 to a positive power, which is 0, divided by h to the first. And when you have a power, when you have same bases to the powers divided by each other, you subtract the powers. You get the limit as h goes to 0 of h to the 1/3 minus 1. 1/3 minus 1 is negative 2/3. But we know that's the same as the limit as h goes to 0 of 1 over h to the positive 2/3. And if you plug in 0 for h, you're going to get 1 over 0, which doesn't exist. So this limit doesn't exist. And the reason this limit doesn't exist is because what happens here is we actually have a vertical tangent line at this point. If you graph the cube root of x, cube root of x looks like this. And it has a vertical tangent line at the origin, right? So the slope of the tangent, so in fact, this kind of goes along with some other things. But if you try and graph the derivative of this, which I will, since it's kind of something a lot of you asked about. So this is my f of x. Even though I'm going to pretend like I don't know what it is, we know it's x to the 1/3. Here's what the derivative would look like. So here's what I think about when I'm trying to graph the derivative of a function from the graph of a function. I think about, okay, well, if my function's increasing, my derivative is positive. And I really kind of imagine just drawing little tangent lines. So if we wanted to, let me grab a pen that's kind of trash. So I could draw like a tangent line here, and here, and here, here, and here, and here. And right at the origin is the vertical tangent line going through the graph. And then here, right? So I'm thinking about drawing a bunch of tangent lines and thinking about their slopes. So first of all, I notice all of my tangent lines in this graph have a positive slope. And hopefully you guys can see that kind of all right, I hope. And I notice that over here, the slope is pretty small. So that means my derivative is going to be fairly small and positive. So maybe it's like here. And then I can see that as I move to the right, my derivative is getting a little bit bigger. So my y value for my derivative is a little bit bigger. And then a little bit bigger, a little bit bigger. And then it looks like it's going to get super duper big, like infinitely big, right? If your tangent line is a vertical tangent line, your slope has an infinite or undefined slope. So that this function is getting infinitely large. Or I should say this derivative is getting infinitely large. And then on the other side, it's infinitely large, and then it gets slightly less large, slightly less large, slightly less large. So it's kind of doing the opposite thing, like that. And although this isn't perfect, it's a good guess as to what the derivative actually looks like. So, and we can do a couple more examples of this, but this is my general kind of method of attacking how to take or how to get the derivative of the graph of the derivative from the graph of the original function. You're thinking about what do the slopes of the tangent lines look like? Are they positive? Are they negative? Are they relatively large? Are they relatively small? Okay. So this function, derivative undefined at 0, vertical tangent line at 0. But now I want to ask the harder to ask question, which is how do we find the derivative of this function? Well, we know it's supposed to be 1/3 x to the negative 2/3. But how do you do it using the limit definition? Because I will tell you, sometimes people ask this question. Because we would like to at least verify to ourselves one more time before we just kind of move away from the limit definition, right? So occasionally we're going to come back and say, oh yeah, limit definition for maybe for the derivative of e to the x or the derivative of a trig function. For the most part, we're going to be like, derivatives, we have rules for that. But for one last time, we're going to verify one of them. So, no, not the last time. So the derivative of x to the 1/3 is the limit as h goes to 0 of f of x plus h, which is x plus h to the 1/3 minus x to the 1/3 all over h, right? Which we had down here. And then we said, well, we're going to do it at 0 so it's easier and get non-existent. So how do we deal with this thing? It's kind of a mess. If it was a square root of x plus h minus a square root of x all over h, we would multiply the top and bottom by the conjugate. Well, there's something kind of like that for a difference of cube roots. Here it is. It's not pretty. We're going to multiply by the following thing. I might have enough room here. We're going to multiply by x plus h to the 2/3. Let me make sure. Like, what are we multiplying by here? Yeah, that's right. A squared. Okay. Plus x plus h to the 1/3 times x to the 1/3 plus x to the 2/3. All over the same thing. You might ask, with good reason, where the heck is this coming from? Well, here's where it's coming from. It's coming from the knowledge about how you factor a difference of cubes. If you're going to factor a cubed minus b cubed, it factors as a minus b times a squared plus a times b plus b squared. So what I've done is I've taken these pieces and made them these pieces. Here, this is your a, and this is your b. This here, x plus h to the 2/3 is x plus h to the 1/3 squared. So that's your a squared. This is your a times b. And this is your b squared, right? X to the 1/3 squared is x to the 2/3. So here's what I've got. I've got a minus b times a squared plus a times b plus b squared. And that's exactly equal to a cubed minus b cubed. So here's what I get on top. And I could multiply it out, but I really don't want to, unless you guys really want me to. Yeah, it's super cool. It's the limit as h goes to 0. On top, you're going to get a cubed minus b cubed, which is x plus h to the 1/3 cubed, also known as x plus h, minus x to the 1/3 cubed, also known as x. The denominator is just the denominator, right? It's garbage. I mean, it's not total garbage, but it is what it is. The denominator is that times all that. Again, we know we want to cancel that h out, so we don't multiply it through. We leave it as h times all that stuff. If you really want to, or if you're really not convinced, you can FOIL out the top. It's kind of a pain though, right? You're going to get this times that, this times that, this times that, minus this times that, minus this times that, minus this times that. And all the middle terms cancel out. So you get like 6 things and 4 of them all end up canceling. Okay. Sorry, you guys are like, why did you say this is super cool? Because some of them sent me a private chat saying that's super, that's really cool. So yeah, it is really neat, even if you guys don't know. Ah, come on. All right, so the top is just x plus h minus x, which is just h. I'm going to try and make my life not terrible. I'm going to say the top is just h. If the limit is h goes to 0 of, right? In fact, I'm going to be really kind of lazy about this. So that's x plus h, that's x. So this whole top, that's just x plus h minus x, which is h. And then, holy smokes, we can cancel some stuff. Right, we're always trying to cancel out that first h in the denominator. Then we end up getting, limit as h goes to 0 of 1 on top over all this garbage here. X plus h to the 2/3 plus x plus h to the 1/3. Oops, that should be an x to the 1/3. Sorry, I made a little mistake there. Plus x to the 2/3. Finally, we let h go to 0. So we get 1 over x plus 0 to the 2/3, which is x to the 2/3, plus x plus 0 to the 1/3 times x to the 1/3 plus x to the 2/3. So look what we have. We have x to the 2/3 plus x to the 2/3 plus x to the 2/3, which is 3 times x to the 2/3. And with 1 over 3 times x to the 2/3, or if you want to bring the x up to the numerator, 1/3 times x to the negative 2/3. Well, how about that? That's exactly what the power rule would have given us. So, no one should ever ask you to do this, but it is something worth seeing. You could totally do this for other root powers. Like you could do this for the 4th root or the 5th root. There are equally gross things, or actually I should say there are more gross things you could multiply by to make it so the top comes out nice. We don't want to do that. We want to just use the power rule. So then we just start applying the power rule to things willy-nilly. That's right, willy-nilly. Like, for example, I could say f of x is equal to, so I'm actually going to throw in some extra rules here, like x to the 17th power plus the 5th root of x. What's the derivative? So, word of wisdom, whenever you're taking, well, most of the time when you're taking a derivative, it usually is beneficial to simplify the expression first. I definitely want to write this as x to the 17th power plus x to the 1/5 power. Then it's much more clear to me what I have to do to take the derivative. The derivative of x to a power is that power times x to the 1 less power. Same deal here. The derivative of x to a power is that power times x to the 1 less power. 1/5 minus 1. It's perfectly okay to write 1/5 minus 1, but then you should simplify it. So 1/5 minus 1 is 1/5 minus 5/5, which is negative 4/5. So this ends up being f prime of x is 17x to the 16th plus 1/5 x to the negative 4/5. And so one of the rules that I used here without, so I should actually back up a little bit. We talked about the limit rules a while back and how like we kind of use them without saying them all the time. There are some derivative rules that we kind of use in the same way. And one of them is the sum rule. It says if you're taking the derivative of a sum of functions, it is just the sum of the derivatives, right? So if you're taking the derivative of things, add or subtract them together, you basically just take each derivative and then add or subtract them together. Let's look at the longer example. let's say we want to take, let's say our function g of x is equal to 5 times x to the 8th plus 2 over the square root of x plus, I don't know, sure, the 4th root of x to the 7th. What else do I want? Minus 9 over x to the 3rd plus 5. Okay. So here's the way we're going to take the derivative of this. Well, first, actually, before we do anything, we're going to simplify this. So here's a point of carefulness. If you should only be doing one thing at a time, meaning you should only be simplifying, or we should only be differentiating. We shouldn't try and do a little bit of both. I've definitely seen people be like, okay, well, the derivative is 40x to the 7th plus I'm going to simplify this. It's not good to do that, right? We want just all or nothing. So let's just simplify. If we're just simplifying, it means we're not actually changing anything. So it's still the function. It's not the derivative yet. So it's still 5x to the 8th. This is going to be 2 over x to the 1/2, or 2 times x to the negative 1/2. This is going to be x to the 7th to the 1/4, which is x to the 7/4. And this is going to be minus 9x to the negative 3rd. And then if you wanted, although I don't really want to, you could write this as 5 times x to the 0. I don't think we need to do that, but you could. I'm going to leave that there for a second. I'll erase it in a minute. So now that I've written this all as things times x to powers, I can use the power rule. Now, there's a rule I'm about to use that I haven't even talked about. That's okay. What's the derivative of 5x to the 8th? It's 40x to the 7th. Because the rule I'm using that I'm not saying I'm using is the constant multiple rule, which says that if you have a multiple of a function and you're taking its derivative, you just get the multiple of the derivative. Really, the way I should actually be thinking of this just for a moment is it's 5 times the derivative of x to the 8th, which is 8x to the 7th. We almost never do that. Right? We just say, oh yeah, the 8 comes down, it multiplies the 5, and then you get 40 times x to the 7th. But there are times when it's useful to think about, oh, it's really this constant that hangs out is what I would say. You say constant multiples hang out. So you get this multiple hanging out times the derivative of the function. Same deal here. I'm going to get 2 times the derivative of this, which is negative 1/2 x to the negative 1/2 minus 1 is negative 3/2. Same thing here. So here I'm actually not, so you could write it as minus 9 times minus 3x to the minus 4th. Or you can just say the minus 3 comes down, multiplies the minus 9, you get plus 27. X to the minus 3 minus 1 is minus 4. But again, I'm really getting that from doing, oh yeah, it's minus 9 times minus 3 x to the minus 3 minus 1. That's what's really happening there. And then for the last part, if we have a constant just by itself, its derivative is 0. But if you really want to, you can think, oh, it's 5 times x to the 0, and the derivative is 5 times, bring the power down, 0 times x to the negative 1. But it doesn't matter what that is because 0 times anything is 0. But I really think the better way to think about this, and so I really want to prevent any confusion. When you have a constant just by itself, its derivative is 0. The way you can think about it is, well, what does y equals 5 look like? It looks like a horizontal line. And the horizontal line has a slope of 0. So the derivative of a horizontal line is a 0. On the other hand, a constant multiple doesn't have a derivative that's 0. Or it does if you want to start talking about the product rule, which we can talk about a little bit later. But the idea here is you just get the constant times the derivative is the easier way to think about it.
Did you accidentally miss out the x to the power of 7 over 4? Or Was it like on purpose?
Yes, no, it was not on purpose at all. I totally missed it there. Yeah, sorry about that. There should be, let's just squeeze it in there. Sorry, that's a, let me make some room here. Yes, good call. This should be, so let me actually write this down how I would actually do it. 2 times negative 1/2 is negative 1 times x to the negative 3/2. And then this would be, so the 7/4 comes down, you get 7/4 times x to the 7/4 minus 1 is 7/4 minus 4/4, which is 3/4. Yeah, thanks. Appreciate it. And then I would simplify my answer a bit. So I'd get 40x to the 7th minus x to the negative 3/2. Right? You could write minus 1, but we usually don't if the coefficient's just 1. Plus 7/4 x to the 3/4 plus 27. You can either write 27x to the negative 4th, or you can write 27 over x to the 4th, and there's good reason for writing it both ways. I would definitely write it this way if I was going to have to take a second derivative, right? Because I want to write it as x to a power. I would definitely write it. In fact, let me actually. So I think this is a perfectly good way of writing this answer. This is the better way to do it if you have to take repeated derivatives. On the other hand, it would also be perfectly legitimate to write it so everything had positive powers, meaning 40x to the 7th minus 1 over x to the 3/2 plus 7/4 x to the 3/4 plus 27 over x to the 4th. Writing it this way makes it more clear that 0 is not in the domain of this derivative, or that this function is not differentiable at 0. Writing it this way is less obvious. Writing this way is like, oh yeah, of course x can't be 0 because you can't divide by 0. I want to find the derivative of S equal to force over area. I think that's how that's written. Yeah, to compute dsdA for a constant force of F equal to 5 newtons when area is equal to 2 meters squared. So while I will say that this question is probably phrased in a moderately confusing way, it doesn't have to be super confusing. So I'm trying to find the derivative of this. Now, when I see this, this tells me a lot. This tells me that S is my function and that A is my variable. And everything else doesn't really matter. So when I see S equal to F over A, I'm really thinking, oh, F is a constant. In fact, they even tell me in the problem that F is a constant force of 5 newtons. So I could start making my life a little easier by writing this as 5 over A. Because as far as we're concerned, the force in this problem is 5 newtons over the area. And I don't remember what S is supposed to represent. Force divided by area is probably something like, pressure, maybe? I don't know. I'm not so good at all the physics stuff. It's okay, this is math. Speed, oh, sure, yeah, I got, because maybe
I'm just guessing because it's the S. I don't know.
Yeah, but
No, it would be velocity,
force
right?
is mass times acceleration. So I don't know. I'm not too worried about it. Force is meters per minute. No, it doesn't matter that much. We're not worrying about the units or whatever it's supposed to represent. We're just worrying about doing what they ask us to do. That's not always a great perspective. In this problem, it's a fine perspective. But yeah, you're right. It's good to think about. It is good to do some dimensional analysis sometimes to see if your answer actually makes sense. It especially comes up when we talk about related rates. That's when it's kind of like, oh, do these units kind of match what they're supposed to? Which we'll get to probably sooner than we want to. Some of you, I think, already have gotten there. So we want to take the derivative of this. I might rewrite this as S of A is 5 over A, or even more easily, S of A is equal to 5 times A to the negative first. Because then I'm writing it as a power, and I can take the derivative using the power rule. You could also use the quotient rule here. I know we haven't talked about it yet, but I imagine some of you have. So I can find the derivative S prime of A, or if you prefer, ds dA, power rule time. 5 times the derivative A to the negative first is negative 1 times A to the negative 1 minus 1, which simplifies as negative 5 times A to the negative 2. And I would probably further simplify it as negative 5 over A squared. But we're not done, because the problem didn't say just find the derivative for a constant force of 5 newtons. It said find the derivative or compute ds dA, the derivative, for a constant force of 5 newtons when A is equal to 2 square meters. So then we have to additionally say, oh, I'm going to plug in and find S prime of 2 square meters. That's going to be negative 5 over 2 squared, which is negative 5/4. And I don't really have a good idea of what the units are on that, but I do know that that's the right answer as far as we've done what they've asked us to do. Yeah. So the point that I'm trying to make is not really about this problem. The point I'm trying to make is it's good to simplify things so that we can take the derivative easily. We're probably, we need a couple of things before I can really do that. So, for example, if my function y was equal to, I don't know, x to the 8th minus 2x to the 5th plus the square root of x, and maybe 3 times the square root of x plus 2 over x to the 4th. I want to find dy dx. And I could, you could, we could use the quotient rule once we've learned it if we haven't learned it. Chain rule actually is not super applicable here. Not a bad idea, but the chain rule is more when you have a composition of functions. And although it's certainly possible to write this as a composition of functions, it's kind of not really what we're going for with this particular problem. The idea instead, although we're definitely going to talk about the chain rule too, is that we should simplify this thing. When you've got a fraction and you've got a denominator that's just one term, you can simplify this whole thing as each thing divided by that one term. It's kind of like how with the limits, where you got the limit as h goes to 0 of stuff with h's over h, you can divide each of the terms that has an h in it by h. I can divide everything here by x to the 4th. I can totally write this. Now, here's what I shouldn't do. I've seen a lot of people do this. I'm going to make a mistake. It's a very tiny, not important mistake, but I'm going to fix it. I could divide each thing by x to the 4th. So you x to the 8th over x to the 4th minus 2x to the 5th over x to the 4th plus 3x to the 1/2 over x to the 4th plus 2 over x to the 4th. Here's the mistake I made. It's not a big deal, but it's a big deal to me. I didn't find the derivative yet. I've done no differentiating. All I've done is simplify. If all you've done is simplify, I shouldn't be writing that that's what the derivative is, because it's not. It is what the function still is. So, and I'm maybe more of a stickler for this than some people, but it's good to be a stickler for things. We want to use the right names for things, right? This is still the function y. We've only simplified it. We haven't changed it anyway, so we should still be calling it y. I'm still going to simplify even more. X to the 8th divided by x to the 4th is x to the 4th. Right? We subtract the powers. 2x to the 5th divided by x to the 4th is 2x to the 1st. 3x to the 1/2 divided by x to the 4th is 3x to the 1/2 minus 4 is negative 7/2. Right, because it's 1/2 minus 8/2. And finally, 2 divided by x to the 4th is 2x to the negative 4th. And now we're in a position where we can use the power rule for each of these parts. Now I'm going to write the derivative. And you can write y prime, and you can write dy dx. whatever you like. Derivative of x to the fourth is 4x cubed. Derivative of 2x is 2. So the derivative of negative 2x is negative 2. And again, you can use the power rule there. And this is negative 2x to the first. So the 1 comes down, you get negative 2 times x to the 0th. And x to the 0th is just 1. Or you can just say, this is a line with that's negative 2x, and the slope of a line y equals negative 2x is just negative 2. Basically, when you have a constant times x, the derivative is just the constant. Here, it's not as nice. You get 3 times negative 7 halves, so it's going to be negative 21 halves times x to the negative 7 halves minus 1 is negative 9 halves. And then here, 2 times negative 4 is negative 8, x to the negative 5th. Negative 4 minus 1 is negative 5. So that's what we want to do here. We want to, if we can, simplify things so we don't have, like, you could totally use the quotient rule here, but it's really gross. It's really much nicer to simplify this if we can first, and then just use the nice, easy power rule. Not that that's always an option, but if it is an option, I encourage you to use it. Let's see here. No, I said there were very, so I feel like we should probably start. Yeah, okay. There's like 5 different things I want to do right now. I'm trying to think of the right direction. So what I really want to do is talk about the product rule and the quotient rule and the chain rule. But to talk about any of those things, I kind of really feel like we need a couple more types of functions we are able to differentiate. Right now, we really only have a rule for differentiating x to a power. And while that's nice, right? And you could totally like be like, I'm going to take the derivative of x to the 3rd times x to the 5th using the product rule. And you could. And we will probably after we learn the product rule. But it seems really silly to not just simplify that and write it as the derivative of x to the 8th, which is 8x to the 7th. Here's what I will say about this. You could not differentiate this doing the derivatives of the products multiplied together, or sorry, the product of the derivatives, right? I want to really, 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 really stress that this is not equal to the derivative of x cubed times the derivative of x to the 5th, which is 3x squared times 5x to the 4th, which is 15x to the 6th. So I'm going to say again, you cannot take the derivative of a product of things by doing the product of the derivatives. That does not work. That is incorrect. But before we can really earnestly talk about the product rule, I feel like we need like 3 other derivatives. And so, yeah, let's go ahead and talk about those 3 other derivatives. And this will actually kind of tie back into one of the other things I want to talk about, which was, which a lot of people asked about, which was finding the derivative of the thing based on the graph. So, yeah, I guess we should go slightly in the order of the book. So I'm going a little out of order because I'm going to do a couple trig functions. But before that, let's talk about the derivative of e to the x, which I imagine many of you already know is e to the x. And this derivative, so your book does some weird thing about, they talk about any base, and then they do this other limit thing. I'm going to show you a better way, maybe. I don't know, a different way for sure. So, as we often do when we're talking about a function we don't know how to differentiate, we go back to the limit definition. So that's going to be the limit as h goes to 0 of f of x plus h. So if this is my f of x, then my f of x plus h is e to the x plus h. Minus f of x, which is e to the x, all over h. And you're right, I'm totally not doing the graphing thing for this one. I'm going to do it for the sine and cosine. So then what most people do, which is not wrong, is to factor out e to the x. So with the limit, as h goes to 0, of e to the x times e to the h minus 1 all over h. And then, since we're talking about h going to 0. E to the x, as far as h is concerned, is just a constant, right? E to the x isn't changing if it's h that's approaching 0. So this is equal to e to the x times the limit as h goes to 0 of e to the h minus 1 all over h. And then this is where things get strange. People talk about how this expression is equal to some constant value L, and it totally depends on what your base is here. So if your base is some other value A, like in the book, then you get other answers. So what is this limit equal to? Well, you need to go back a little bit. So you may have learned, I hope someone has at some point talked to you about where the number e comes from. Here is where it comes from. One of the places it comes from. It comes from limit. Typically, I think of it this way. Limit as n goes to infinity of 1 plus 1 over n to the n is equal to e. That is a limit worth knowing. Those are n's, by the way, not h's. Now, I would imagine some of you probably are like, where does that come from, right? That might not be something you've ever seen before. The way I typically talk about this expression is in the context of compound interest. So if you think about the compound interest, so this is going to be hopefully a short kind of quick little journey aside here. If you think about the compound interest formula, the amount of money at time t is equal to p times 1 plus r over n to the t power. That's the compound interest where you compound, n times t power. That's the formula for compounding interest n times per year. And then you might have also learned, you probably also learned that there's a continuously compounded interest formula, PERT, where a of t equals pe to the RT. And that continuously compounded interest formula comes from letting the number of times you compound interest become infinite. You essentially compound interest an infinite number of times per year. And each time you compound it is with an infinitesimal amount of time. So here's how this boils down. The gist is going to be, I'm going to lend you $1. I'm going to charge you 100% interest for 1 year. So if I do that, the amount of money you're going to owe me after 1 year is going to be $1 times 1 plus my 100% of interest is 1 as a decimal. So my interest rate is 1, which is 100%, divided by n to the n times 1 power. And if you let n be larger and larger, so like if I compound this semi-annually, if n is 2, the amount of money I get, in fact, actually, let me just do it annually. If I compound it once per year, I get my $1 back plus the $1 of interest. You owe me, right? 100% interest. So after, if n is 1, I get $2. But if n is 2, right, if I compound the interest semi-annually, halfway through the year, I get half my interest. So halfway through the year, I get half of 100% of interest, which is 50% of $1, which is 50 cents. So now you owe me $1.50. And then on that $1.50, in the second half of the year, I'm going to charge you 50% interest on that. 50% of $1.50 is 75 cents. So at the end of the year, you owe me $1.50 plus 75 cents, which is $2.25. And so to make a long story very much shorter, if I compound it quarterly or monthly or weekly or daily, every time I increase the number of times I compound it and decrease the time interval with which I compound it in, you end up owing me more money. And the amount of money you end up owing me gets closer and closer and closer to this number E, $2.71 approximately. So the whole idea here is that this limits E. You can also graph it, like if you want to go check out Desmos, you can graph 1 plus 1 over x to the x power, and then look way to the right. To the right. I don't know. To the right, I think. My left, your right. Hopefully that's right. Right. You should see that you have a horizontal asymptote of y equals e, which is 2.7-ish. 2.71828, etc. Okay. If you want to hear more about this story, come see me in office hours. I'll gladly speak on and on and on about it. But the point I want to make is the following. If this limit, so the limit of 1 plus a small thing to a power of a large thing, where the large thing and the small thing are reciprocals. So the large thing is exactly 1 over the small thing, and the small thing is exactly 1 over the large thing. If you have a limit that exactly looks like that, where it's 1 plus a small thing to a power that's the reciprocal of the small thing, that limit's always e. And so it definitely works for this. The limit as h goes to 0 of 1 plus a small thing, h is small, to the reciprocal power of the small thing, 1 over h is large, that limit is e. And you might be wondering, why do we care? Well, because now look what I'm going to do. I'm going to take e and replace it with this limit. Well, the limit's already there, so I don't have to write the limit again. So e is 1 plus h to the 1 over h. Well, it's the limit as h goes to 0, 1 plus h to the 1 over h. So you get 1 plus h to the 1 over h to the h minus 1 over h. But now look what happens. The 1 over h and the h, those cancel out. 1 plus h minus 1 is just h. So you get the limit as h goes to 0 of h over h, which is the limit as h goes to 0 of 1, which is 1. Oh, and sorry, I lost the e to the x in front here. So my answer is e to the x times 1, which is e to the x. Sorry, I got a little sloppy there. So big picture, very condensed. The derivative of e to the x is 1 times e to the x. You definitely do not have to be able to prove that, but you definitely do need to know it. So here's what we've got so far. The derivative of x to a power is n times x to the 1 less power. We also have the derivative of e to the x is e to the x. I'm going to write something else in a minute here. Because I also want you to know the other words. I want you to know the other derivatives of other exponential things that don't have a base of e. So what if instead I asked you for the derivative of 2 to the x? Well, later on I'm going to show you a better way to do it with implicit differentiation. But we don't have that tool right now. So here's how you could do this. Maybe we can't do this. Let me think for a second. Can I do that? No, we can't. We need either the chain rule or, yeah, sorry, I apologize. We can't do this yet. I'll tell you, but I can't show you yet, that the derivative of this is 2 to the x times the natural log of 2. And more generally, the derivative of a to the x is a to the x times the natural log of a. And so, honestly, when I see this, I really think of the derivative of e to the x as e to the x times the natural log of e. But that's just equal to 1, so we don't really write it. Don't worry, we'll definitely show you this later. Okay, I know I'm really working my way back around to the product rule here. The other derivatives I want to show you, which you may or may not have seen, are the derivatives of sine and cosine. And I'm just going to tell you to them right now, but I'm going to show you them. So it is true that the derivative of sine is cosine. I should really say the derivative of sine of x is equal to cosine of x. And similarly, the derivative of cosine of x is equal to negative sine of x. You may be thinking, well, great, like that's not super helpful because you just told me a thing but didn't show me how. Well, let me show you how. I'm going to show you 2 different ways. First and foremost, I'm going to show you the nice way, the way that actually makes some sense. Let me change pens. trying to rotate my pen so I don't just blow through them all. All right, so graphically, yeah, sure. So here's the sine function. I haven't drawn it. Here's about to be the sine function. Has a period of 2 pi. Has a range from -1 to 1. That's pi over 4. It's a little less than pi over 2. It's a little 1. Sure. Looks vaguely like this. So sine starts at 0. At pi over 2, it's 1. At pi, it's 0. At 3 pi over 2, it's -1. And 2 pi, it's back to 0. Come on. And this is a great example of how using the graph to find the derivative is actually really, really nice. So, as is typical with the sine or cosine function, I often like to look at kind of the 5 important points. The highs and the lows and the middles, or basically all the points that are the beginning and ends of quadrants, right? 0, pi over 2, pi, 3 pi over 2, and back to 2 pi, which is one full period. So I'm going to draw myself some tangent lines. There's really, I guess they're like tangent pieces. So here's a tangent piece. Here's a tangent piece. Here's a tangent piece. Here's a tangent piece. And here's a tangent piece. Okay. Now let's start at pi over 2 because that feels a little bit easier. So pi over 2, pi. And I really think if you're trying to graph a function and its derivative, the nicest way to kind of try and do it is to do it where the derivative is vertically directly below it so you can kind of make things match up. So the pi over 2, what's the slope of my tangent line? Well, my tangent line is horizontal, and a horizontal line has a slope of 0. So my derivative is going to have a value of 0. And that's true at pi over 2. It's also true at 3 pi over 2, because at 3 pi over 2, my derivative is also, well, at the tangent line is horizontal, so the derivative is 0. Now, 0, the tangent line is definitely having a positive slope. And the way I've drawn it is meant to be on purpose. It definitely looks like that slope is just the line y equals x. And it is. That slope is 1 at that particular point. And then over here at pi, the slope is definitely -1. And then back here at 2 pi, well, 2 pi should be the same as at the beginning because it's one full revolution or one full period later. I should be back at 1. And those points look like the points that occur on the cosine graph. And I didn't draw it great, but that is exactly the idea, that you can totally see the derivative of sine is cosine by looking at the graph of sine and saying like, well, the derivative values look like they totally match up with the cosine values. And you can also do the same thing for cosine. You can say if I start with cosine, or cosine, yeah, I don't have room down there, otherwise I would just kind of do it. So my function is cosine, which, looks like this. Top, middle, bottom, middle, top. We have the 2 pi, and if we try and draw sine below it, or sorry, if we try and draw its derivative below it, so the slope of the tangent line there is 0. And pi over 2 is a negative slope. Let me draw my little values so they match up. At pi, it's 0 again. At pi, 3 pi over 2, it's +1. And finally, at 2 pi, it's back to a slope of 0, right? I should draw the tangent lines. Boop, boop, doop, doop, doop. And hey, that looks a lot like not sine, but the sine graph flipped over, which is negative sine. Okay. So what to say about this? Good question. So let me ask you guys. Do you want to see the limit definition of the derivative of sine or cosine? Or do you want me to skip that for now and talk about the product rule?
Yeah, let's see the limit definition of sine.
Okay. So the limit definition definitely relies on two limits we have used before. And this is actually the reason why we talked about, well, not the only, but it's definitely one of the reasons. So there are two limits we need to use. One of them is that the limit, I'm going to use h instead of x, as h goes to 0 of sine of h over h is equal to what? Everybody. It works better when there's people in the classroom. I'd be like, you,
Yeah, one.
you, everybody. Yeah, the limit's 1. And similarly, and I know I've definitely seen this in people's homeworks, the limit as h goes to 0 of either 1 minus cosine h over h or cosine h minus 1 over h. This limit's 0. I can talk about this if we want, but I'm going to leave it there for now. So we need those limits to find the derivative of either sine or cosine. Let's do sine. It's a little nicer. So the derivative of sine of x is the limit as h goes to 0 of the function evaluated at x plus h minus the function evaluated at x all over h. Okay. Yeah. We also need one other thing. We need the angle sum identity for trig functions. So it is true that sine of a plus b is equal to sine a cosine b plus sine b cosine a. That's the angle sum identity for trig functions. So I'm going to use that to re-express sine of x plus h. So I'm going to write this as the limit as h goes to 0. So x is my a, h is my b. So it's sine of x times cosine of h plus sine of h times cosine of x minus sine of x all over h. And you might ask now, well, what do we do with all that? Nothing like factors out. So I feel like I'm making a dumb mistake. So no. So here's what we're going to do. We're going to put the two pieces together that happen to have something in common. Sine of x times cosine of h and sine of x. Those at least both have a sine of x. So I'm going to rewrite this as the limit as h goes to 0 of sine of x times cosine of h minus sine of x all over h plus sine of h times cosine of x all over h. Now I'm going to do something. I'm going to factor out the sine of x here. And I'm also going to write the limit of the sum as the sum of two limits. So write this as the limit as h goes to 0 of the first thing plus the limit as h goes to 0 of the second thing. And here I'm going to factor out the sine of x. So it's sine of x times cosine of h minus 1 over h. Plus, here I'm going to rewrite it so that the cosine's kind of factored out. Sine of h over h times cosine of x. All right, help me out. Sine of x is just sine of x, right? H going to 0 doesn't affect that. What's the limit as h goes to 0 of cosine h minus 1 over h? Oh, it's 0. All right. What's the limit as h goes to 0? Sine of h over h. Oh, it's 1. Cosine x still is cosine x. So I get 0 plus cosine x, which is cosine x. So that's how you use the limit definition along with these specific limits to show that the derivative of sine is equal to cosine. And you can do very much the same thing to show the derivative of cosine is equal to negative sine. The only difference is instead of using the angle sum formula for the sine function, you have to use the angle sum formula for the cosine function. Are there questions about this? I imagine there might be, so please feel free to ask them if you have questions about this.
How'd you get cosine h minus 1 over h?
How did I get it, or how did I know its limit was 0?
How'd you get it?
So the way I got it was so I took this piece and this piece here, and then from this piece I factored out a sine of x. So when I factor out a sine from here, right, this piece is, well, I mean, it's really just sine of x times cosine, right? And this piece here is minus 1 times sine of x. So when I factor out the sine, I'm left with the cosine of h minus a 1.
Oh, I see. Okay.
Other questions? I'm pretty sure that this proof is pretty much verbatim in your textbook in section 3.3. Let me take that
real quick.
Oh, no, sorry, it's 3 point something. Go ahead.
Why is the limit of h, as h goes to 0, of cosine of h minus 1 over h equal to 0?
Sure. That's the one thing I thought you guys might really ask about for sure. Because, yeah, so it actually depends on the other limit of the sine as h goes to 0 sine h over h. So let's take a look very quickly. So I would like to throw some product rule example at you guys. So the way you deal with a cosine h minus 1 or a 1 minus cosine h or 1 plus cosine h is you multiply by the conjugate. Okay. So when you multiply by the conjugate, I'm going to get the first thing squared. So cosine squared h. The middle terms cancel. Right? You get a cosine h times 1 and a minus 1 times cosine h. Those add up to cosine minus cosine, which goes away. And then you get a minus 1 times 1, which is a minus 1. Now, this is not exactly how we wish it was, but it's close enough. There's a trig identity. There's a trig identity that comes up a lot. You guys definitely want to know your Pythagorean trig identities. The one I'm referring to here is that sine squared of whatever angle you like, I'm going to use h, plus cosine squared of h is equal to 1. If I specifically want to solve for cosine squared h minus 1, I'm going to say that cosine squared h minus 1 equals negative sine squared h. So then I'm going to rewrite this as the limit as h goes to 0 of negative sine squared h over h times cosine of h plus 1. And then I'm going to break this up into two very convenient fractions. Its limit as h goes to 0 of negative sine of h over cosine of h plus 1 times sine of h over h. Is this the same as that? For sure. Definitely the same. All right, the top times top gives you negative sine squared. Bottom times bottom gives you h times cosine of h plus 1. All right, so now for the final, or the finale, as people actually say. What's the limit as h goes to 0 of sine h over h?
1.
Good old 1. What's the limit as h goes to 0 of negative sine h over cosine h plus 1? Well, it's not like a regular thing, but plug in 0. What's sine of 0?
1. Oh, 0. Sorry.
What's cosine of 0?
1.
So 0 over 2 is 0 times 1 is still 0. So that's why this is 0.
Thanks.
But yeah, and so you may have seen versions of this, like find the limit as h or x goes to 0 of 1 minus cosine of 6x over 4x Same kind of deal. You multiply by the conjugate, you do all this kind of work, and you end up getting 0. Okay, so in the final 10 minutes here, let me get to the point. Well, so the point of some of this is that sometimes there are functions we would like to take the derivatives of, but we can't just simplify things, right? I would really, really, really like to be able to take the derivative of x cubed times sine of x. And I'm going to tell you right now, it is for sure not equal to 3x squared times cosine of x. Definitely, definitely not. I could try graphing them on Desmos, and you would definitely see that the slopes of the tangent lines of this function do not look like the values of that function, because we needed something. So, and it's, again, it's the same reason that the derivative of, I'm using a slightly different example I did last time, the derivative of x cubed times x squared is not equal to 3x squared times 2x. Because we can't take the derivatives of the factors and just multiply them together, right? We know that this is actually the derivative of x to the 5th, which is 5x to the 4th. So what we need is the thing called the product rule, which I'm going to show it to you. I'm going to show you this example, and then I think I can probably, yeah, I'll give you a sweet little proof. So the derivative of a product of two functions, people usually write f times g or f of x times g of x. So the derivative of f of x times g of x is equal to, the way I always kind of say it in my head is the derivative of one thing times the not derivative of the other thing, plus, and then you switch it, you do the derivative of the other thing times the not derivative of the first thing. Or f prime of u, f prime of x, the derivative of f times the not derivative of g, plus switch it, vice versa. There's not a good way to say it. Plus vice versa, the not derivative of f times the derivative of g. So if you're doing the derivative of a product, there should always be some addition. It should always be derivative times the not derivative plus other not derivative times derivative. Let's see if that works for this example. The derivative of x cubed times x squared should be the derivative of x cubed times x squared plus the not derivative of x cubed times the derivative of x squared. Let's check that out. That's equal to 3x squared times x squared plus x cubed times 2x, which is 3x to the 4th plus 2x to the 4th, which, yes, whoops, I wrote 5 before, is equal to 5x to the 4th. So it works. At least it works in this example. But it does work in general. Right? That is actually the, quote, the product rule. Words are hard. And so we can also use that to then say, well, if that's true, which it is, then it should also be true that the derivative of x cubed times sine of x is equal to the derivative of x cubed times sine of x plus the not derivative of x cubed times the derivative of sine of x. I usually skip this step, but it's perfectly fine to write it. That's going to be equal to 3x squared times sine of x plus x cubed times derivative of sine is cosine of x. And that's all we can do. We leave it like that. We don't use it, like you could factor out an x squared from each of these. We almost never do that. So okay, where'd you go, mouse? There you are. Okay. So that's the idea of the product rule, that you can take the derivative of a product of two things by doing the derivative of the first piece times the second piece plus the first piece times the derivative of the second piece. And it's actually pretty straightforward to show why it's true, which I think I should do for you guys. I know what, we'll leave that for next time. Let's just do a few more examples. So let's do the derivative of, say, like x to the 18th power times cosine of x. All right. Derivative of this part, 18x to the 17th times the not derivative of that part, plus flip it. Leave the first part alone. Multiply by the derivative of the second part, which is negative sine of x. And then you should, at least I think you should rewrite this as 18x to the 17th times cosine of x minus x to the 18th times sine of x. Another example. Let's do the derivative of x to the 4th times e to the x. Right? We got e to the x too. So that's going to be, again, and it really doesn't really matter which order you do things in. Right? You could do it as the derivative of that times that plus the derivative of that times that. Since you're adding and multiplying, order doesn't really matter. But I usually like to do it in the order it's written. So I'm going to do the derivative of x to the 4th times the not derivative of e to the x, which is e to the x, plus the not derivative of x to the 4th times the derivative of e to the x, which is e to the x. So I should point out, right? Some people like to write like this is f, and this is g, and this is f prime times g plus f times g prime. It's perfectly fine if you want to do that. A lot of times people do simplify this particular type of one because you can factor out a lot. You could totally factor out an e to the x and an x cubed and write this as e to the x times x cubed. And from here, I'm left with just a factor of 4 because I factored out the x cubed and the e to the x. And from here, I'm left with just a factor of x because I factor out 3 of the x's and I'm left with 1 of them behind. This is a very typical, like, later on, a graphing question where you're able to like find, well, you're able to find where the derivative is equal to 0, which that's a story for another class. One more, sure, why not? Yeah, okay. So what about the derivative of, what about a triple product? What about x to the 5th times e to the x times sine of x, cosine of x? That's already. How do we deal with the triple product? We don't. Well, we do, but we don't. We imagine it as just a product of two things. I'm going to say it's the product of this times this. This is actually kind of important, so hang in there for the last minute. The derivative of x to the 5th times e to the x, I'm just going to write it as x to the 5th times e to the x for a moment. Times cosine of x, right? Derivative of the first thing times the not derivative of the second thing, plus, then we flip it. We leave the first thing alone. We multiply with the derivative of the second thing, which is negative sine. Oh, that's right, cosine of x prime. Okay. Now, for the derivative of x to the 5th times e to the x, we're going to use the product rule again. So this part's going to be the derivative of this, which is 5x to the 4th, leave the e to the x alone, plus leave the x to the 5th alone, multiply by the derivative of e to the x, which is e to the x. And it's all of that times cosine, plus x to the 5th times e to the x times the derivative of cosine, which is negative sine. Okay, I'm going to multiply this out because I want to show you one last important thing about this. So this is, if I distribute the cosine here, I get 5x to the 4th times e to the x times cosine of x, plus x to the 5th times e to the x times cosine of x. I'm going to write plus, although I usually bring out the minus sign, plus x to the 5th times e to the x times negative sine of x. What I really want to point out is that when you have a product of more than two things, it's the same sort of rule, just repeated. So if you think of this as the derivative of f times g times h. The derivative is f prime times g times h plus f times g prime. I know g prime and g are the same here, but it's still g prime times h plus f times g times h prime. So if you have to do the derivative of a product of three things, you get 1, 2, 3 pieces added together, and each piece has one derivative and the rest not derivatives. And you have to get each of the different derivatives. And the same thing is true if you have more pieces. If it was 4 pieces, if it was f, g, h, j, you'd have f prime times the other 3 things, plus g prime times the other 3 things, plus h prime times the other 3 things, plus j prime times the other 3 things. So you always get one derivative and all the other not derivatives multiplied together. And that's definitely going to be important when we talk about the chain rule.